So originally he's from Oregon in the US. So he did his undergraduate studies there in mathematics, physics, and computer science at Oregon State University. But then he moved a few states further to Colorado, where he did his PhD in Boulder at the University of Colorado. For those who don't know it, it's at the foot of the Rocky Mountains, a very
pretty
nice place indeed. On the topic of magnetohydrodynamics of massive stars. He then moved on to do a postdoc at the High Altitude Observatory, still in Boulder, and currently he's doing a second postdoc, as you see on his title page, in France, in Paris-Saclay. So, Kyle, we are very happy to have you here, and I will give you now the floor.
Thank you very much, Joris, and everybody else. Okay, well, some of you know me, some of you don't. But today I'll be talking about a project that's been kind of ongoing for the last couple of years or so. And basically, the idea is to look at how does convection excite waves? In particular, looking at rotational influences and most recently with magnetic influences. And so this is one of my favorite kind of title slides just because everything fits together so well. So I use it all the time, but it's appropriate here too. And so what you're seeing is a 10 solar mass star. It's a simulation in the core where you're seeing the magnetic field threaded there. So you can it's cut across the equator. So you're looking at convective columns that have been kind of cut in half. And the colors indicate kind of blocks of field strength. So white is about 100 Gauss, blue is about 100 kilogauss, and red is about a megagauss. So you get some pretty whopping fields in the core. It's main sequence, so kind of given by the layout. And of course that convection excites waves, but on this kind of, on this diagram, it's hard to see the amplitude of the magnetic effects on the waves, for one, because the initial magnetic field was 0. But in any case, let's move on. So I'll give a little bit of more motivation, looking not just at stars, because what I'll be talking about is applicable to many different systems. Then I'll talk a little bit about how we can go about modeling convection using heuristic models and a little bit with some numerical models. And then I'll talk about how we can combine these convective models to have wave convection interactions, specifically really looking mostly at the analytical side of things, since Tammy and company really deal a lot more heavily with the numerical stuff. So. Then I'll talk just a little bit about how we can go about including magnetic effects into these analytical models and just conclude from there. So one of the most basic experiments, but a really beautiful one, that I think anyway, is just a tank of water that's chilled at the bottom and heated at the top, or just kept at room temperature at the top. And what this does is that water has this really interesting property that right around 4 degrees Celsius, you have a transition in from convectively unstable to convectively stable. So in the region where you're convectively stable, so let's see if can you guys see my cursor or not? I don't know.
Yes, we can.
You can see it? Okay, good. So in this region here, this is that stable region, and this is that convective region. It's a relatively low Reynolds number, but fairly high Rayleigh number, which means that it's relatively tractable from a computational standpoint. So you can really have a nice comparison between these physical experiments and numerical experiments, as well as some theory. And so what you're seeing on this, this graph here is really the probability distribution at those 2 points. So one is the convective region, where of course you get a big spread in the probability distribution because you have turbulent processes going on. And then, and this is also for the temperature fluctuation. And then you have a much more narrow distribution for the temperature profile of the waves, of the wave region, wave driving region. And over here, let's see, can I minimize this? There we go, okay, great. Over here, we have the turbulent spectra. So this is in frequency space, not K space. So the power spectra are a little different slopes than what you're typically used to in K space. Again, power spectral density, basically of the velocity, I believe in this, or maybe, sorry, so of the temperature again here. So you can see in the convective region, you have, because it's not extremely turbulent, you still have some resonance of the most unstable modes, this being the most unstable mode. And then in the wave region, you have, of course, different spectra because, well, they're waves. Okay, so another, not convectively driven exactly, but another possibility, of course, are wave-driven or wind-driven gravido-inertial waves, or they call them near-inertial waves in geophysics. And so what you're seeing here are, again, time frequency and power spectral densities of clockwise and counterclockwise vortices in the Sea of Japan. And again, you can see very nice peaks corresponding to the inertial modes, and then some sub-peaks corresponding to some additional spreading of those modes. But very strong signals of gravido-inertial waves. So this, I think, is about 300 meters below the surface, so quite far from the driving region. So this is one reason why the signal is so clean. Recently, I just kind of ran across this the other day when I was putting this talk together. I was like, oh man, there's some Juno results I missed. And so here we're looking at just a couple of examples of wave-like structures, more like wave packets than long propagating or standing waves, something like that. But you have your typical gravity waves or gravido-inertial waves. Here, for instance, an interesting wave train, maybe a Lie wave or a combination of a Lie wave and some inertial oscillations or convective oscillations in that region. And again, some more beautiful gravity or gravido-inertial waves here. And the interesting thing was that they included in this paper, at least for me that was curious, was if you look at the shearing regions, where are you finding most of these wave-like structures? And you find them in these regions of relatively high shear, although I suppose this is really a coverage issue that you don't have a lot of coverage at these the super high shear point here. I'll be talking about how this result at the end of the talk, but I just wanted to introduce it here because it's a pretty neat result. This work between Coralie Niner, myself, Stefan, Umin Lee, and Casey Lovekin. Maybe there's one more. And the idea here was that there was a particular star, this HD 49330, which exhibits these occasional outbursts. I think they're relatively periodic. I'm not entirely sure about that. I was more on the theory side of things, but basically it provided us a means of trying to use a global mode analysis to ascertain what the expected frequency spectrum is versus the observed one. And as you can see, they're relatively close, and the observed modes are probably suppressed relative to the simulated modes up here. But the analysis, this global scale analysis that we did, does a pretty good job of describing at least the rough location of these modes and a little bit of their spread. And of course, we have your local work with Dominique, both from last year and from this year, describing these nice bumps and nice high amplitude, low frequency regimes, which kind of points either to really low frequency gravity modes or maybe also to some gravido-inertial modes. I'm not sure what the rotation rate of these guys is typically, but at least it's cool because it's in a low frequency regime, which is where it needs to be if there was to be some rotational influence. Okay, so on to convection. Let's just say convection is really hard. It's a turbulent process. Turbulence is hard, especially in astrophysical regimes. Typically, you're either in extremal Prandtl number regimes. The Prandtl number is the ratio of the local viscous diffusion to the thermal diffusion. So in stars, this is typically quite small, of the order of 10 to the minus 5 or even lower sometimes. And these are regimes that are really tough to get at numerically. You can do a little bit of analytical work in asymptotics and quasi-linear theory to try to get at those regimes, or at least some qualitative structures that might exist in those regimes. But another thing in stars, of course, is they're highly stratified, which means that you have scales all over the place, and it depends upon where you are in the star. Most of it's non-analytical, so like I said, it's turbulence. So you can do some statistical analyses, stochastic analysis of certain kinds of equations to try to get at what sort of distributions and PDFs you expect from the turbulence, but describing the turbulence analytically is still not yet tractable. course, that's a clay math problem, so good luck with that one. So there's lots of different models, lots of approaches. I'll just talk about one or two today. But for simulations for the numerical side of things, you can typically do about 1 billion. Sometimes if you really push things and do a maximal type of simulation, you can do 1 trillion, trillion points in your simulation. But for a star, of course, you need something like 10 to the 27. So, you know, computer size of the universe sort of problem. So what you're seeing down below there is some of my thesis work. So the idea there was coupling different regimes. So on the left, you have a global scale simulation called case F. It uses a code called ASH. It's a spectral code. It's anelastic, which means it filters out sound waves. So everything you're seeing there is just really hydrodynamics minus the acoustic field. And you can kind of see these large scale structures that align north-south. You of course have downflows that are dark and upflows that are light, which means your upflows are much more space filling, but typically much slower. And you have your fast downflows that punch through the convective zone. Now this is somewhere in the mid-convection zone, if I remember correctly. And then you have a 40-degree square simulation using code that I built as a PhD student that shows kind of super granular scales. And then if you go to the photosphere, you have even smaller scales. And really it's just trying to show this hierarchy of scales that you get as you move closer and closer to the surface. Of course, one reason that you don't have that sort of north-south alignment in these other two simulations is that effectively the Rossby number, or the ratio of the average velocity to the average length scale and the rotation rate is relatively large, which means that they're not rotationally constrained and the Coriolis force doesn't play much of a role. And one thing for all of these systems is that because we can't fully resolve the system, we have to figure out a way to try to close that system. So a way of trying to describe the scales that we don't resolve. You either just, of course, try to chop them out. You can have some sort of backscattering scheme in which you try to send power both up and down the energy spectrum. Those are very complicated models, something like Smegorinsky-Lilly, or you can just have a diffusive model, which is like a large eddy simulation. Which means that you basically, if you have a star, you're basically simulating lava instead of plasma. Okay, but as far as modeling goes, analytical modeling, you can go way back to Boussinesq in 1877, who had one of the first closure models with a turbulent viscosity. So this thing that I was just describing, this kind of LES type of model for shear turbulence. But the one that we're interested in is thermal convection. It was first done by Taylor in 1915, then followed on independently by Schmidt and Prandtl. But basically the idea there is that you can linearize the system of equations in certain regions and then describe the heat transport through an eddy model, which is basically like mixing length, which of course is our standard model, right? Most of you guys have probably seen this if you've dealt with stellar evolution in any sort of way. This is originally attributed to Bohm-Vitéz, 1953, but Ed Spiegel does a nice description of it as well. Basically, there's just a couple of ingredients. You need to describe what the heat flux is. It's based, and it's dependent upon a parameter lambda, which is your mixing length, which is something that you have to feed into the model. It's only one of the parameters. There isn't actually another one. And it's also dependent upon the local superadiabatic gradient. So if you're very superadiabatic, you'll have a high convective flux and vice versa. This gives you your convective velocity based upon a few other stellar parameters, basically kind of the radiative flux, the local thermodynamic state, the gravity, and again, your mixing length parameter and the superadiabaticity. Now there's one more assumption, and this one kind of gets glossed over sometimes, and it's really the closure assumption of this model, and that is to look at how much excess heat is carried over this distance lambda relative to the change in the background state. And Bohm-Vitéz sent this to just 2 times the background state. So if any of you are curious where that 2 came from in the equation, well, that's where it came from. It's just a choice, but one based on some experiments and a little bit of theory. Of course, you can extend these things, and many people have done that. These aren't that commonly used, which I still find surprising because, I mean, what, this is 70 years old. So there's Spiegel's work, so the one that I mentioned, which both introduces the local version of mixing length, but also a non-local one. So this allows for things like overshoot and penetration to be taken into account, because you can basically have the parcel cover very many scale heights, very many mixing lengths. Basically, it's just an integral differential equation. It's a little bit more complicated to solve, but I don't know, might be worth playing around with if anybody's interested. And then Goff did it is a conference proceeding, I believe, in 1977, but it is so extensive that I always have to put it in these talks. There's something like 30 or 40 pages of all the different possibilities for mixing length and adding in new like thermochemical, thermal halide processes, all sorts of things, pulsating atmospheres, and actually even adding in rotation, which is interesting because that's what we're talking about, and so many more, like so many, it's crazy. But so the one that I want to talk about is super simple. It's looking at Rayleigh-Benard convection. So that means it's unstratified, or nearly unstratified, in terms of the convective region. It's basically a hot plate, cold plate experiment. You can do it either in the presence of gravity or not. Here we're doing it with gravity, of course, because we want to look at little parts of stars. And the idea is that, of course, you have your initial system, which is this, you have your cold plate, your hot plate, and a linear stratification between, which is represented just by pure conduction, which gives you this profile. And then if the Rayleigh number of this thing is high enough, or really if the diffusivities of the system are low enough, you can push this to convect. And if it convects, that means that you basically wipe out that temperature gradient in the interior of the system, and then you have small boundary layers. This is the system that we want to look at. So there's quite a few different people who kind of really pioneered theoretical work that I consider very interesting for the problem at hand. One of the first was Malkus in 1954. It was based also on some experiments, but I'll talk about his work just a little bit more. And it was really Townsend that did a lot of the experimental work that Howard and Spiegel then built upon to build better monomodal or modal convection models, which is exactly what this is about. So Malkus basically said, okay, we have this really turbulent system, and we want to break it down into pieces that we can try to describe analytically as best as possible. So his principle is basically to look at the heat flux. So this is the average of the temperature and the vertical velocity, and describe it as a modal decomposition. So it's basically kind of like a Fourier series. So his basic principle is to produce this heat flux, his constraints on the system, is one that the mean temperature gradient has to be negative definite. I mean, it's always decreasing. There's no weird bumps and stuff in it, which basically is equivalent to saying that you have a very equilibrated system. There's actually a finite number of modes that contribute to the total heat flux, and the reason for that is that you have a dissipation, a diffusivity in the system, and eventually that will mean that at some point you'll have zero motion or zero temperature perturbations, and at that point you truncate your series. And this last mode is basically on a scale that is just marginally stable. So its local Rayleigh number is close to the critical Rayleigh number, or just slightly below the critical Rayleigh number. Okay, so the basic implications of this are you want to maximize the heat transport, because this selects which modes to consider. So that's another kind of choice in this model. Provides a model for the mean and fluctuating temperature as well as the velocities. And it actually provides pretty good approximations to experiments compared to self-similarity arguments like Kolmogorov, for instance, because it is buoyantly driven. So if you're going to Kolmogorov, of course, you break some of the assumptions of Kolmogorov, namely the homogeneity and the isotropy assumptions there, really just isotropy. But yeah, so that was kind of the originating work, but there's another path to getting at this problem. This was pioneered by Howard in 1963. So basically the idea there is this is a bit more mathematically sophisticated, so you can eliminate some of those basic assumptions. And the idea is that you really just end up with a buoyancy work equaling dissipation, which is just your energy equation, and that you have a balance between the heat flux and the conduction, which are the only two possibilities in the system. if you have a very low viscosity. And it also provides a mathematically concrete maximization principle, which is key. Okay, so I've been talking about this heat flux. So that's this guy here. So if you have this, so what you're seeing here is half the domain effectively. So here is where you'd expect the temperature gradient to be constant. Then here you have your boundary layer here. And these are the contributions of a bunch of modes. The fundamental mode is this smoothest mode here. And it is really the one that packs the most heat. It carries the most heat by about, I think the next mode is 30. So this mode is about 50%. Next mode is 20%, and it decreases from there. What we'll be talking about is really just the fundamental mode, because we want just estimates of things. We're not considering the super precise estimates here. We want scaling. So we pick that one. And then what you're seeing on the right side are temperature perturbations, again, as a function of away from the boundary layer. Here you have your boundary layer in your interior. And the symbols are measurements inside of a Rayleigh-Benard convection experiment. And then the black line is the fundamental mode approximation to that. So it does a pretty reasonable job for a turbulent system with only one mode. So basically you've reduced this thing to an algebraic system that simply describes a highly nonlinear PDE system quite well. Impressive. Okay, so I talked a little bit about Rossby number earlier. So this, if you're confused about the definition, here you go. So it's basically that average velocity divided by the rotation rate and some average length scale. So in a stratified system, for instance, if you have see that cyclonic vortex near the surface and it falls down through the convection zone, becomes anticyclonic as you reach the base. And that's really just due to a pressure influence, but also a little bit due to Coriolis forces acting on the downflow. And again, here you have a global scale model of flows. These are convective flows where the upflows are orange and the downflows are dark. So this one's near the surface. So there you have, again, you have much more isotropic sort of flows. And then as you go down in the convection zone, you recover those more aligned structures due to the Coriolis force that forces them to be aligned with the rotation axis, partly due through the Taylor-Proudman theorem. That's the global scale. So what about this local scale? So we're talking about Rayleigh-Benard convection in a box so far. So what you're seeing here on the top are lab experiments. I don't remember what the substance it was with. Maybe it was water with a particle in suspension, so you can actually see what the turbulent flows look like. And then you have DNS of these direct numerical simulations of a similar system. And basically what you see are different kinds of structures. So in this first one, you have these fairly laminar structures. They form Taylor columns effectively, so where you're in a geostrophic balance. So that's a balance between basically the derivative of the vorticity and the temperature gradient or the entropy gradient. And as you push the system harder, you become increasingly turbulent until you reach something that looks like a geostrophic turbulent system where you don't really have any permanent structures, but on average, you still end up with a columnar-like structure. And you see very similar behavior in 3D numerical simulations. So that's encouraging. Okay, so on to this heuristic model of rotating convection. The one I mentioned before, Malkus's model, is really one that's focused on non-rotating convection, so we have to figure out a way to extend it. And how we do that is we again maximize the heat transport, but the new assumption that we make, because we've added new forces into the system, is that we say the velocity is basically the, let's see, what's the next one? Yeah. So we say the velocity is related to those growth rates from that eigenvalue problem here. These are basically just eigenvalue. So that the velocity is related to these linear growth rates divided by some length scale of the system. So in order to do this, of course, we have to maximize the heat flux. And if we crank through all the math and do the eigenvalue problem, you end up with a relation that says the heat flux or the convective heat flux is this expression. And all you do is maximize this thing, and it basically gives you a relationship between velocity, or really the flux, and this quantity z, which is your eigenvalue. And so what you can do is then you, for this simple model where you've chosen only this single mode, this heat maximizing mode, you can describe the superadiabaticity of the system, the velocity of the system relative to the mixing length velocity. And then this is your eigenvalue. It's not really an eigenvalue problem. It's just an algebraic problem for this value z, which is really proportional to your wave vector to some power. Anyway, so the idea here is that in this plot, you're seeing a couple of these quantities as a function of convective Rossby number. So above Rossby number of 1, these things basically all, the solid curves all tend towards 1, which is what you'd expect. They latch on to the non-rotating system. The dashed lines are just asymptotics. And then here you have your, so this A is related to Z in terms of, I think is A is Z to the 3/2. And that basically just gives you your horizontal wave vector scaling. So that increases, yes, the horizontal wave vector increases as you increase the rotation rate. So it just means that your convective structures, your convective columns that we saw earlier are just becoming smaller and smaller. And interestingly, in order to compensate for that, because we basically have kept the heat flux constant through the system, because that was one of the criterion of this, is that you have a drop in velocity to compensate for that. Okay, so that's the model. So how does it stack up against numerical simulations? So we've seen that it works pretty well in non-rotating systems and experiments. Rotating experiments are pretty hard to do, and I don't know of a really good one yet. They're working towards it. But so one way you can get around that is to do numerical experiments, and this is one done by Adrian Barker 6 years ago. And basically it says, so if we're looking at omega here, omega is basically the Coriolis number or the inverse Rossby number, which says that these quantities, so like the temperature gradient, the temperature perturbations, and the velocity all scale very closely to what you expect from this monomodal model. So in recent work, Laura Curie, who I don't know if she's still at Exeter, maybe she still is there. So those simulations of Adrian's were all done at the pole, a very special place, but doesn't allow you to test the latitudinal dependence of this model. So what you can see here are a couple of, is the temperature field at 45 degrees colatitude and the vertical velocity field at 45 degrees latitude. And you can see the tilting of the structures because of Coriolis force. So these are actually pretty hard numerical experiments to do because you end up getting kind of a shearing box and you have to figure out a way to get around that. But basically the idea is that if you look at a function of latitude, the temperature gradient in these experiments, so these are these symbols here and their variance in time, and then a couple of different modal models. So Stevenson's model, I believed, is the dashed line here. And the best fitting multimodal model, so if you include more modes in the expansion of your heat flux, that's that solid line here, so it does a little better. But again, since we're really only considering kind of order of magnitude things in terms of scalings, this change by a factor of really just a quarter or something, or maybe even 30%, is inconsequential for what we want to talk about later. But when it comes to doing better in terms of these models, there's actually some nonlinear models that we can do. So this was works by Ian Grooms back in 2010, where they basically form an eigenvalue problem from a quasi-geostrophic system and allow you to fit, so this is a simulation, but the model allows you to fit these structures extremely well. But because they're laminar, it allows you to have more isolated structures. If it's extremely turbulent, you can consider it more as an average of that stochastic system. And since I'll be talking a little bit about global systems later, one of the possibilities to moving beyond Kolmogorov in those systems is to look at something like Emmanuel Domrey's work from a few years ago, these quasi-linear global scale models, hydrodynamic still, or just the models of Bussy from 2002, where you have these kinds of structures, these banana cells, as we call them, or pancake cells. So those basically are just the most unstable mode in azimuth for a given Rayleigh number, or a given level of driving. Okay, so those are a collection of models, but really we're focusing on that single mode model of convection. And we want to figure out how this can impact waves. So getting back to that picture in the beginning, of course, we know convection drives waves in stars, which is why we see modes at their surface anyway. Whether that's core convection or other driving regions, that's of course up for debate. So on the left, we have a massive star where you have this convective core that's driving waves, just a schematic sketch of a spiraling out gravity wave. And then we have on the right, some work from Lucie Alvan, where this is a solar-like star that drives gravity modes in its interior, and you get, of course, a lot of beating and interference because many modes are excited. But there actually are distinct modes in there. They're fairly linear, but a very nice model nonetheless for looking at global scale mode excitation. And I know Tammy's group is building on that stuff as well. Okay, so we'll be talking mostly about gravito-inertial waves. So these are modes that are below the buoyant frequency, the Brumm-Fieseler frequency primarily, and they're definitely more in this lower frequency. You can push up there, but to the super, I don't know even what to call them, the super gravito-inertial waves where their frequency is above the Brumm-Fieseler frequency. Your inertial frequency is just twice this local rotation rate. And of course, if you are, you can also, because it's a gravito-inertial wave, you can push down to a lower frequency. Okay, so now we're going to return to this experiment, this convection experiment, because it gives you an idea of what possibilities you have for driving. So this is work by Daniel from about 5 years, Daniel Leakene from about 5 years ago. So up on the right, again, you have your experimental apparatus for which this numerical simulation is its numerical analog. So that's a cylinder, and this is a 2D simulation, but the dynamics are relatively similar. And what you can see are two kinds of very prominent things in this time series. So you have this dark region here, which is the interface between the convective region down here and the wave region up here. There's the convectively stable region up here, where you have your waves that are being driven. And what we're going to look at are two possibilities for wave excitation. So our analysis doesn't tell you which is more important, but it tells you how they scale with Rossby number and various other parameters. But what Daniel found was that interface deformation is not as important as Reynolds stress driving. Okay, so Reynolds stress driving is what happens, so these waves, they have an evanescent tail down in this convective region, which means they interact with that convection in a non-local way. So basically these waves fill the volume of the convective driving down here much more strongly than you might expect. And so what you end up with is, at least in these numerical experiments, an interfacial deformation that contributes to wave driving of about 30%, and the rest being Reynolds stresses. Okay, so we've got this simple Boussinesq system. Don't worry too much about the equations, there's there for eye candy. So basically we're taking a piece out of a sphere and we're making it a nice little Cartesian box where gravity is in the vertical and the rotation vector tilts in the direction of y. We also have a direction chi that will be important later, which just describes the direction of the plane wave propagation that we'll be looking at. So here you have your rotation terms in the momentum equation, of course your pressure balance. You have your buoyancy terms in the vertical velocity equation, pressure balance, Coriolis force. It's Boussinesq, so like I said, there's it's incompressible rather. So you don't really have any influence of change in density in terms of the continuity of the system. And you have your buoyancy equation. Basically, you can combine these in a clever way and find a dispersion relationship that links your wave frequency to your wave vectors. And you can play around with a bit of complex analysis, complex algebra, and find what the convective flux should be in terms of those frequencies and wave numbers and the wave velocity. And that allows you to then get an estimate of what the convective, what the wave flux should be through the interface and in the radiative region. And one of the first really nice analyses of these were by Press in 1981. So there are a few constraints in using this model of Press. So this is really focused on interfacial excitation. So in this region here, in this boundary between the convective and radiative regions. So one of the constraints is that for efficient excitation, you need to have your wave frequency close to the convective overturning frequency. And you also need pressure continuity across that boundary. So if we use all of those assumptions and we use our monomodal rotating convection model, we can get an estimate for what the wave flux should be. And that looks like this. It's a little two-line equation. It's not too bad. But basically, it shows you that that flux should be proportional to the cube of the ratio of the rotating velocity, mixing length velocity to the non-rotating mixing length velocity times some functions of the wave Rossby number. And that wave Rossby number is dependent upon the convective Rossby number, so the mixing length velocity, the non-rotating one, to the rotation rate, and the non-rotating length scale of the system. And then there's this factor S in there. So this is an important one. This is basically the ratio between the Brunt-Väisälä frequency in the radiative region and the overturning frequency in the convective. So for stars, this should be big, right? 10 to the something, 10 to the 3, 10 to the 5. What exactly it is, it's a little tricky to tell because we don't really know what the structure of that transition looks like very well. But basically what we can find using this is that if we look, so sigma here is your frequency, your wave frequency, normalized by the Brunt-Väisälä frequency. You have your convective Rossby number. And so at a large Rossby number or slow rotation rates, you don't have too much change in the fluxes. So this is, again, that ratio. So the convective, the rotating flux to the non-rotating flux is basically identical in this region. But as you transition below a critical Rossby number, where your wave Rossby number becomes less than 1, you start to decrease that flux significantly by orders and orders of magnitude for these interfacial waves. So they become pretty inefficient at transmitting via interfacial waves. So one thing that we can look at if we integrate over frequency for a certain value of S, this is the value of S of 1,000, and we're looking at a wave propagation angle of 45 degrees, which is just going to be arbitrary. Basically, you can just scale this if you choose a different wave propagation angle, and it's at 45 degrees latitude. That again just changes the overall amplitude of things, so that doesn't really affect this ratio. But what we find is that if we look at this flux for a ratio of the rotation rate of the star to the breakup of that star, you can show that at low rotation rates, you have a fairly high flux. It decreases, you have a resonance at, this depends upon S. So that this will shift depending upon what your stiffness is. And then it decreases significantly, not to 0, but to just a few percent as you go towards breakup. So why is this? Well, the reason is that you have critical latitudes. So if you're only considering gravido-inertial modes and nothing with differential rotation or magnetism, you basically focus your waves into a very small latitudinal region, which is why the overall flux ends up going down, because you're integrating over all volume here. Okay, so that's the interfacial stresses, or the interfacial wave fluxes. What happens if we look at the Reynolds stresses? So this problem is a bit more complex. I'll put a little bit more math in this one, just so you can kind of get a feeling for how to derive these sorts of systems. So what we're looking at here is the wave equation, which can be derived. And this is basically how you derive your dispersion relationship. It can be derived from that original system of 5 equations that we saw earlier for the Boussinesq system. So what we want to do, because we want to get an idea of what the amplitude of these waves are, is we have a time-dependent amplitude, and we basically have, it's a modal decomposition of the total velocity and projected against the eigenfunctions of the system. So nominally, this system would be non-separable. So this is where you can make a choice about whether you want to take the traditional approximation, where you only look at the radial component of the Coriolis force, or more generally, you can make a choice in the eigenfunction that allows you to make the equation separable again. And that's this little function here. It's quite simple. Doing that, you can then solve the system. And oh yes, so what you have here is your source function. So this includes all your Reynolds stresses. If you have them, there's entropy stresses or the buoyancy stresses, but those are typically small in these systems, even in stratified systems. So we'll only really consider the Reynolds stresses in this term. And that looks like this. So it's basically your Reynolds stresses here. And so what we can do to get these amplitudes is after plugging in this function into this, you get a system you can solve for the average amplitudes that involves basically a convolution of your wave function, your eigenmode, versus the time derivative of that source function and some normalization factor. And this can basically just be expanded this way, and you can see it's a pretty simple convolution of the source function, these Reynolds stresses, and the eigenfunction. Okay, so since we're looking at a simple system where you only have, there's no functional, basically it's just a Heaviside function for the Bernoulli-Parcella frequency, namely it's some large value in the radiative region and then the small convective value in the convective region. This means that you just need to solve a system of equations. It is very familiar. Just a second order Poincaré system with two domains. And so in order to patch these together, we just have to patch them at the boundary condition at the base of the convection zone or the top of the radiative region. You just assume continuity and of C1 continuity, or namely the continuity of the function itself, and then also of its derivative, or effectively like the pressure. So then we have a couple of different eigenmodes for the system that can be solved for very simply and analytically. So in the radiative region, you have this eigenfunction. So that's just a sinusoid with some weighting. It's based upon the boundary conditions. And in the convective region, you have a sine and a cosine, just again to match the boundary conditions, which means that you have a dispersion relationship that ends up looking like this. So it's a bunch of tans and linears times those tans to give you your frequency as a function of k, or k as a function of frequency, whichever way you want to look at it. But basically this implies that there's discrete modes in the system. Likewise for the super inertial modes, so these are the ones where the frequency is above the inertial frequency. You have very similar functions, so you have a sinusoid in the stable region, but they are evanescent, and hence sinh and cosh in the convective region, and with a similar kind of dispersion relationship, which again implies discrete modes. Okay, so with this we can go back to computing our wave flux. So this is basically just the average of the imaginary part of the product of the vertical velocity and the pressure, typical definition in wave problems. If you go back and derive what those are and plug them in, this is what you get. So you can see there's a pretty strong scaling with the horizontal wave number. Basically, again, get this term here, which is your transform of the source function, or the convolution of your source function with your function. So right now we've left things pretty general. So this will work for any source function, but that could mean that that integral is non-analytic. But since we're keeping everything analytic, we just go with that monomodal model, which is basically just a complex function, a sinusoid, if you take the real part. If you do that, and you look at this wave flux for a variety of parameters, so this is again your Reynolds stress driven, rotationally influenced wave flux to the just pure gravity wave flux or the non-rotating wave flux. And for a pretty strong stiffness, you can see that relative to that gravity wave flux, which could be small, you can have a very large increase in the overall flux of the system for subinertial waves, and a modest one of up to maybe about 30 times for the superinertial waves of for modest Rossby numbers of about 0.2. So again, here we're at high Rossby number, so slow rotation. Up here, we're at low Rossby number, or fast rotation. So this says that an intermediate range of Rossby number, and this actually is pretty typical Rossby numbers for stars, about 1/10 to 100th. You can have a pretty significant amplification of gravido-inertial wave transmission relative to gravity wave transmission. So that's pretty exciting. But you also see, of course, this peak structure. So it's not uniform across Rossby number. There are certain Rossby numbers for which you get this, this amplification. But as you go towards lower and lower Rossby number, of course, you get a much larger number of possibilities in terms of Rossby numbers that will lead to an amplification. Similarly, if you decrease that stiffness, you can still have an amplification, but it's not as large. It's down by, in this case, a factor of 10 to the 5. So yes, this thing scales as s to the -2. So it's a very strong effect. So it gives you, might be an interesting way of trying to ascertain what the stiffness of that interface is. If, of course, it presumes that there's a relatively sharp transition. If there's a soft transition, the story could change, and it's something that we can look at in the future. And lastly, if we look at a really soft transition, you can see that actually the situation is somewhat reversed. You can actually have a dampening, really just less transmission, not dampening, of the overall wave flux coming into the radiative zone. Okay, so just to kind of summarize that little bit, for stiffly stratified systems, we have a large flux relative to the gravity waves, and that scales as s to the -2. However, this flux declines with Rossby number, with decreasing Rossby number, very strongly as Rossby number to the 5th. But this is consistent with the behavior of the interfacial flux, just occurs at slightly different Rossby numbers. In the end, as you increase your rotation rate, you tend to decrease your flux. But for the interfacial flux, the stiffness plays less of a role. So what about implications for stars? Where might these waves be important? So if we look at a couple of relatively low mass stars, straddling the sun, we do higher mass stars, just need a grid of models to do that. These are models from Louis Amarre. And basically, if we look at the trace of the Rossby number at the base of or near the base of the convection zone as a function of age. So here we're PMS, usually typically very rapidly rotating and transitioning towards the zero age main sequence. You can see that when you're super rapidly rotating, you're in this regime where these waves may not have as much flux as you might expect. But as you age just slightly, you can move into a regime where they start to become more important for transport processes. And as they age, it actually becomes increasingly important up in this, again, this Rossby number regime of 10 to the -1, 10 to the -2. Except for the higher mass stars, where the convection, the outer convection zone, I should say, is has very fast flows and hence pretty typically high Rossby numbers. Okay, so what about global scales? So we've looked at this local scale model and kind of ascertained, the nice thing about that is you can really do parameter sweeps very easily. It's all analytical. You just plug it into Mathematica and you get a plot. It's great. But if we look at a global scale system, of course, it's more complicated. But you still have a very similar kind of forest wave equation. The operators are just a bit more involved. So again, you have your source term, which this is basically focusing on the work from Corley and Stefan from just earlier this month. But basically, there's several more terms that come into play here because we're dealing with compressible fluids. There's stratification. There's non-adiabatic effects in terms of having a non-zero entropy gradient. And basically, one way to get at solving this system is just to use the typical RST basis, expand everything out. And then like I showed you earlier, you basically can just integrate that source function versus these eigenmodes. In this case, we're using velocity, which actually looks like this, but that's just a derivative effectively of time derivative of the displacement eigenfunction. And if we play a similar game, like I said, if you just integrate that source function, which has several components, against that eigenfunction, there's some normalization, which in this case is just mode inertia with some weighting factor. You have contributions from the Reynolds stresses. Unlike the previous analysis where we neglected the entropy term, or really the buoyancy term, because it's not highly stratified. In this case, you actually can have contributions of this closer to the surface. There are centrifugal terms that come into play. And then there's interference between all of these source terms. And of course, if you have magnetic fields, it just complicates everything even more. But this gives you the mode amplitude. So like before, you can get at the fluxes using a similar kind of analysis where you just take the imaginary part of the vertical velocity time, or in this case, the radial velocity times the pressure field. So then you can basically use, depending upon what you do for your source function, you can get out what your expected frequency spectrum should look like. And so if we go through if you look in the appendix of that paper, you'll see these huge integrals, like some of them are 3/4 of a page long, something like that, really messy, really complicated integrals. Nonetheless, those things are all evaluated numerically anyway. But what's important here is what you choose as your turbulence model. And what we decided on was a Kolmogorov-like turbulence. So it's not purely Kolmogorov. It's a modified Kolmogorov turbulence where you allow for helicity in the system. So this means it can be non-anisotropic. So this would be like following Goth 1977, different paper though. And in this case, we chose maximum helicity because this thing's rotating really quickly. So the driving should be quite helical. Even at large scales, and even at small scales, rather. So what we're looking at, as we saw earlier, is the expected amplitude in millimegs for a structure that we think is appropriate for HD 49330. We looked both at 1D and 2D stellar structures. This one is computed for the 2D stellar structure, I believe. So these are the simulated frequency spectra. The dotted lines are when it's quiescent, so you get a shift in the overall frequency spectrum between when it's in an outburst, so when you're getting a lot of outflow off of the atmosphere into the disk, circumstellar disk. You have this sort of high amplitude frequency spectrum, and it goes into a more quiescent state where you have less overall mode excitation. And the reason for that is a bit complex. You can make some hypotheses about it, but because we don't know precisely where the driving regions are, it's a little difficult to say precisely what's going on. There's a nice cartoon in the paper if you guys want to see what we think might be happening. But anyway, this is, oh yes, down on the bottom we have the observed frequency spectrum. So as you'd expect, since it's observed, you can't have quite as dense and resolved a frequency spectrum as you could get with a simulated spectrum. But overall, they tend to match pretty well in terms of the expected regions of peaks. So we're pretty happy with that. Now, well, of course, one thing that I mentioned is we can change the global models. And this gives us a way to actually test what the convection or whatever the driving source might look like, which if it is convection, we can change our convection models to see how that can influence the spectrum, give us a handle on what those structures might look like. Okay, So one last piece, I'm not sure where I am for time since I can't see the clock here. Getting real close to the end, so maybe I'll just I'll omit the magnetic fields, and we can talk about that if you want, and just go on to those conclusions. Let's see here. Yep. So we looked at a broad range of things. I showed you some examples of fun wave problems. I'm really excited about the experimental ones, since you have pretty good hands-on ways of dealing with those, and they're pretty simple systems as long as you're using fluids that aren't too complex, like plasmas or some compressible gas. If you're just using water, it's pretty fun. So we looked at a couple of different kinds of convection models, but really focused on this one called a modal convection model, where you basically do something like a Fourier transform on one of the nonlinear products of the system, namely the heat flux, and apply some maximization principles to that to get out a pretty simple algebraic model for the velocity of that mode, the superadiobaticity that's expected in the system, averaged in the system, and the overall wave vectors expected in that system in terms of the horizontal wave vector versus the vertical wave vector. So we can use these to play around with different kinds of driven wave systems. We looked at relatively simple ones. We can look at the magneto-gravito inertial wave problem as well, just adding in another force and another set of parameters, but the framework is the same. Basically, you have a wave equation with a source term. You integrate against, if you can find the eigenfunctions, you integrate against the eigenfunctions, you can get an idea of what those scalings might be. Some future directions will be looking at better modal models, like the one I mentioned by Laura Curie, where you look at multi-modes. You can also look at models built, nonlinear models built based upon the statistics of simulations, like the one from Ian Grooms, where you build this eigenvalue problem that gives you the radial structure of a columnar flow, for instance. This, like I mentioned just a minute ago, this permits you to maybe access what the nature of the convection or the driving source might look like if you can match the spectra up better. And then lastly, of course, magnetic fields. I always play with those. They're always a complication, but fun. So I think I'll stop there since it's been close to an hour or 50 minutes or whatever.
Thank you very much, Kyle.
You're welcome.
Okay, so if anyone has any questions, please mention your name in the chat, and I'll call out your name.
Let's see.
Alex, please. Oh, okay, Dominic, please.
Hi, Kyle. It's Dominic. Thanks for the talk. Lots of interesting avenues, and it's nice to see these things. So I have a more observationally oriented question, as you might expect. Okay. So BE stars, I see a great potential for BE stars in the near future, and this is because we're getting lots of very interesting observations of BE stars. Back in the Corot era, there was very few, and there was only one, I think, observed by Kepler. So TESS is giving us lots of BE stars. What do you want observers to give you? Because BE stars can be quite diverse. What would be the biggest constraint that we can provide you for BE stars?
If you just provide a spectra, that's it. I mean, like I was showing you, if we have this spectra like these, we can apply this global scale model, and this will give us an ability to try to get at what the source function is that's driving these things. So we can look at what's happening both during quiescent periods and during outburst periods to see if there's any change in where the driving is in terms of, say, radius. I mean, it's a big kind of inverse problem, but as long as you just provide us a long time period spectra, then we should be able to play around with that and get some interesting physics from the source function.
Yeah. Okay, that's interesting to know. So it's not terribly problematic that we to put it simply, we wouldn't know necessarily whether the star is in quiescence or not.
Yes. Well, I guess as long as it's like this BE star, there's an apparent change in magnitude in those modes. I don't know if this is generally true of BE stars, but I would imagine that, oh, maybe not. You can tell me. observationally, do you see if during an outburst, is it generally brighter?
Yeah, from a very small sample size, that generally is true, yes.
Okay.
But the problem is that you have to be lucky enough to catch the star in quiescence,
Yes.
which I have no idea what the probability of that is, because the periods of these outbursts can be quite long.
Can be long, yeah.
Yeah.
Like, I think this one's 80 days or something, if I remember right. So it's relatively fast, but relative to your observation window, maybe not so great.
Okay, that's great. Thanks.
Yeah, thank you.
Okay. Anyone else wanting to ask a question? I actually have a question myself I would like to ask. So I tend to look at models a bit from a statistical point of view. And so you explained us that the full model is not tractable. So you need to have some approximations thrown in.
If you want to do it either numerically or analytically. If you can come up with an experiment to do it on Earth, that'd be great. But those are usually very hard.
Yeah.
But yeah, generally you have to truncate it somewhere, right?
Yeah. And so what I was asking myself is, do you introduce then also free parameters, let's say configuration parameters? And
sure, yeah.
The reason why I'm asking is if you would compute the Bayesian evidence, which basically tells you how predictive your model is. For example, on the slide that you are showing now, suppose that the amplitudes would be double and the frequencies would be all shifted with 5 cycles a day to the right. Would you be able to configure your model in such a way that you would still be able to match the observations, because you have
sure. I mean, part of the free parameter here is we don't know the full structure. So if we could, there's a lot of parameters to tweak just in that. You know, what species do you introduce? What rotation rate do you choose for your 2D stellar model? What processes do you include? Do you include magnetic processes to include additional diffusion? Yeah, there's a very large number of free parameters in this system.
If you would have access to your dream set of observations, what would they be to be able to constrain all those parameters?
Well, we can't even really fully constrain the sun, so I guess the best would be to send a satellite to another star. That's my dream.
Okay. Okay, thanks. Anyone else would like to ask a question? If not, then I would like to thank Kyle again. Thank you very much. And I'd like to give
Thanks for listening.
the floor now to Matthias.